Welcome back. Today I'd like to talk to you about the chain rule. And this isn't the chain rule that we talked about in Calculus 1, although it's very much related to it. We're going to be talking about the chain rule specifically if you are taking a derivative in more than one variable, but those variables might depend on a common parameter like t. So let's read this definition together and just kind of talk about what this is saying. So let's start up here. If w is equal to f of xy has continuous partial derivatives f sub x and f sub y, and if x is specifically a function of t, and y is also a function of that same parameter t, and they're both differentiable functions, then the composite function, so we could write this function now w as a function of really only t, because I could plug in a function of t for x and I could plug in a function of t for y. Then that function itself is differentiable with respect to t, which makes sense, and the way that I could compute the derivative is the following, and this is kind of the big idea, is that I can compute the the partial derivative with respect to x and multiply it by dx dt, and then I add on taking the partial with respect to y and multiplying by dy dt. Okay, so this is our chain rule in, really we're only in one variable here in some sense. The only variable is t, but f itself is written in terms of x and y, which are both functions of t. Okay, I think that the best way to go about really figuring this out is to see an example. So let's do an example. So let's use the chain rule. To find the derivative of w is equal to x times y with respect to t along with sorry, not with, oh geez, along the path x is equal to cosine of t, y is equal to sine of t. Okay, what is the derivative's value at t is equal to pi over 2? Okay, so we've got this function w, and the function w has two variables involved, two independent variables, x and y. But both x and y are functions of t. So one of the ways that we could go about computing the derivative of w with respect to t, so what we'd like to find is dw dt, is I said that we could take the partial of this function f with respect, I want my little squiggly partial, with respect to x times dx dt plus the partial of f with respect to y times dy dt. Okay, so let's just do this one step at a time. first, what is the partial of f with respect to x? Well, f itself is x times y. So if I take the derivative of xy, which is sitting right up here, with respect to x, I just get y. Okay? And then I say, and what's the derivative of x with respect to t? Well, the derivative of x with respect to t, well, here's x in terms of t, and the derivative of cosine of t with respect to t is negative sine of t. And I realize that I have y's and t's showing up in the same place, which isn't so great, but I'll fix that problem in just 1 second. Plus the derivative of f now with respect to y, so we're back up here again, and the derivative of the function with respect to y is x, and the derivative of y with respect to t, y is sine of t, and the derivative of sine of t is cosine of t. Now let's write that all in terms of t. Y is sine of t, so I get sine of t times negative sine of t plus x, which is cosine of t, times cosine of t. So if you like, I could write that this is cosine squared t minus sine squared of t. And now, the question here is, by the way, if I wanted to use like an identity, cosine squared of t minus sine squared of t has another way of writing it. I could write this as cosine of 2t if I really wanted to. And the question is, what is the value of that derivative when t is pi over 2? So I could say, what is dw dt evaluated at t is pi over 2? And I would get that that's just cosine of 2 times pi over 2. But cosine of 2 times pi over 2 is just cosine of pi. And cosine of pi is otherwise known as negative 1. Okay, so here is my derivative of w with respect to t, or equivalently cosine of 2t using a trig identity. And if I plug in the value t as pi over 2, I just get minus 1. Okay, so that's how we can use the chain rule to help us to find the derivative of something that's written in two variables, but each of those variables can be rewritten in terms of like this third parameter, maybe in this case call it t. Okay, this can be done just as easy in 3 dimensions as with 3 variables as it was with 2 variables. So for functions of 3 variables, the chain rule is that dw over dt is equal to the partial of f with respect to x times dx dt plus the partial of f with respect to y times dy dt plus the partial of f with respect to z times dz dt. Okay, so if we add in a third variable to our function, nothing really changes. We just have to add on this extra term, which is a partial of f with respect to z times dz dt, and everything works basically the same. Let's do a quick example of that so we can see how it would work with 3 variables. So example, let's find dw dt if w is equal to x times y plus y times z, and we have that x is cosine of t, y is equal to sine of t, and z is equal to t. All right, so just using our new rule now, we can figure out what dw dt is. So dw over dt would be equal to, well, first I want to take the original function and take its partial derivative with respect to x. And if I take that partial with respect to x, I think you'll agree that I get y. But y is, maybe for the first iteration, I should just put in y. Then I need to multiply that by the derivative of y with respect to t. Oh, I'm sorry. The derivative of x with respect to t. I'm sorry. So x is equal to cosine of t, and the derivative of cosine of t is minus sine of t. Plus, now I want to take the derivative of the original function with respect to y, which is x plus z, and then I want to multiply that by the derivative of y with respect to t, which is cosine of t. And finally, I want to take the derivative of this original function with respect to z, which is y, and then I want to multiply that by the derivative of z with respect to t, which is 1. So now I can rewrite and take out the x, y's, and z's, and I get sine of t times negative sine of t, which is otherwise known as negative sine squared of t. Then I get x, which is cosine of t. Cosine of t plus t times cosine of t, plus y, which is sine of t. And so I have computed my nice derivative. If I wanted to, I guess I could just distribute this cosine of t to these two to write it in a little bit simpler fashion, but I don't think that ultimately that's going to help us out that much. So that's good enough for me. Okay, so that is a great example using 3 variables instead of 2. Now, if we have w is equal to f of xy, and x is equal to another function of 2 variables, let's say r and s, and y is equal to another function, let's say a function of, let's say, r and s itself, then the question is, how could we now take the derivative? So let's say that w is defined by x and y, but x is defined by r and s, and y is defined by r and s. Do we get some similar chain rule? And the answer is yes, we do. And the way that we do this is the following. We say that the derivative, or maybe in this case, we get a partial derivative, because we can't take the derivative of w with respect to r outright. It's a partial derivative because there are 2 components to it, r and s. So we can talk about the partial derivative of w with respect to r. And the way that we would do that is we would take the partial of w with respect to x, and then multiply that by the partial of x with respect to r, plus the partial of w with respect to s times the partial of, I'm sorry, I made a mistake. So the partial of y. So I want the partial of w with respect to y times the partial of y with respect to r. Okay, because I'm trying to find the partial of w with respect to r, so I can break that up into two components, kind of the x component of that partial and the y component of that partial. Okay, so if I do it this way, let's take an example now so we can see this in action. Let's write this out. I have an example. Let's find the partial of w with respect to r if w is equal to x squared plus y squared, where x is equal to r minus s and y is equal to r plus s. All right, so the way that we could go about this is we could say that the partial of w with respect to r is equal to the partial of w with respect to x times the partial of x with respect to r plus the partial of w with respect to y times the partial of y with respect to r. So let's plug in the pieces. The partial of w with respect to x is just 2x. The partial of x with respect to r is just 1. The partial of w with respect to y is 2y. And the partial of y with respect to r is 1, coming from here. Okay, so we end up with 2x plus 2y, but x itself is a function of r and s, so this is 2 times r minus s plus 2 times r plus s, which I could simplify down to 2r minus 2s plus 2r plus 2s, which is just 4r. So the partial of w with respect to r is 4r. Okay. Now, let's look at a different situation. We could also have w be a function of x, and we could have that x is a function of r and s. Then we have that the partial of w with respect to r is going to be the derivative of w with respect to x times the partial of x with respect to r. Okay, let's do a quick example that shows how this works. So if we have w is equal to, let's say, 3x squared, and x is equal to 2r minus s, then let's find the partial of w with respect to r. Well, the partial of w with respect to r should be the derivative of w with respect to x, which is 6x, times the partial of x with respect to r. But this partial of x with respect to r is 2. So this is 12x. But if you want that in terms of r, then you should plug in what we know that x is, if you want it in terms of r and s. So you get 12 times x, which is 2r minus s, which is 24r minus 12s. And we get the partial of w with respect to r. Okay, so these are different situations that you can come up with where you want to use a chain rule of some sense. Now, you could just go ahead and plug everything in. Like you could just take this x, which is a function of r and s, plug it into the function, and now you have a function of two variables in which you can take partials. But just understanding that there is a chain rule, just like there is in the calculus of one variable, you can use the chain rule to compute these derivatives and partial derivatives as well. Okay, so a really fun application of this that comes out is a way of computing partial derivatives. A way of computing implicit differentiation. Okay, so do you remember implicit differentiation from Calculus 1? And implicit differentiation was quite hard. It took a lot of algebra, and it isn't so nice. But let me write down. So suppose that you have a function f of xy is differentiable. And that the equation f of x comma y equals 0 defines y as a differentiable function of x. Then, at any point where capital F sub y, or the partial with respect to y of capital X, is not 0, we get the following: that dy over dx is going to be equal to negative the partial of capital F sub x over capital F sub y. In other words, capital F's partial with respect to x divided by capital F's partial with respect to y. And this is always true if the partial with respect to y is not 0. And this just makes these problems extremely simple, okay? And so let's just do one of these and just remember kind of what this was like, and then see how easy this formula makes it for us. So a quick example to show how effective this solution is if we have sine of xy plus 3x squared is equal to 0. Find dy dx. And what I just said is that dy over dx is equal to negative the partial of capital F with respect to x and over the partial of capital F with respect to y. Okay? We need that negative in there. But now let's take the partial of capital F with respect to x, and we get, let's just look at this first term right here. The derivative of sine is cosine, so I get cosine of xy, and then I need to multiply that by the derivative of x times y with respect to x, but that's just y. And then I need to add on the derivative of 3x squared with respect to x, which is 6x. then divide that by the partial with respect to y. Well, the partial with respect to y is going to be cosine of x times y times the derivative of x times y with respect to y, which is x, times the derivative of 3x squared with respect to y, which is 0. And so we're done. So this would be my dy dx. And notice I didn't have to go through all the nasty algebra that I used to have to go through to find an implicit derivative. So that's a very kind of nice application of these partial derivatives. It's kind of fun. Okay, time for you to do some homework.